This video is in continuation with the previous video. In the previous video, we calculated or we found that where this formula for the accumulated value comes from. In this video, we'll see where the formula for this present value comes from. So again, the premise is the same. I make annual installments of C at the end of each year for n years, and compound interest of R% is calculated annually at the R annually is it's the R% compound interest is calculated on each and every installment. So I get this accumulated value. But the present value of all my installments is given by, again, this weird looking formula. So we'll derive this over here. So the crux is the same. We look at each and every installment, basically the present value of each and every installment that we make. So the first installment we make is at the end of the first year. So its present value will be it will be C divided by 1 plus I, right? Because I'm making this installment C at the end of the year, so its present value would be this. You can think of it this way: if I were to multiply this by 1 plus I, I would get a C, right? Because multiplying by 1 plus I is like calculating the interest, calculating that amount after interest over 1 year. So if I were to multiply this with 1 plus I, it would become C, and that is actually what I invest at the end of the year. So this is my present value of the first installment that I make. The second installment that I make is at the end of the second year. So its present value will be nothing but C divided by 1 plus I squared, and so on. Yeah. So the nth installment that I make at the end of the n years is its present value will be C divided by 1 plus I raised to n. So this basically forms the crux for the proof. If you break your total present value into present value of each installment, this is what you get. And clearly, if you see that this is again a geometric progression, it's a geometric sequence with first term C into C divided by 1 plus I, and a common ratio of 1 divided by 1 plus I, because we have a factor of 1 plus I being multiplied in the denominator. So if I recall properly, my formula for the geometric sum is A into, now I'll use the other formula, it's a bit succinct here. It is 1 minus R raised to n divided by 1 minus R, where A is my first term and R is my common ratio. So if I were to write this sum over here, this would be my first term is C divided by 1 plus I, and for the numerator in this term I will have 1 minus R. Now my common ratio is 1 divided by 1 plus I. So 1 divided by 1 plus I raised to the nth power divided by 1 minus 1 divided by 1 plus I. Now again, this might seem a little horrifying, but if you simplify it carefully, it will be good looking. So the numerator is what we want in the formula. If you look carefully, the numerator is actually 1 minus, it's just 1 plus I raised to the negative n power, and that is what is there in my formula. So this is I don't want to disturb this. In the denominator, it is nothing but if I shift this over here, it becomes a 1 plus I minus 1. So it is nothing but I, and also we have a 1 plus I in the denominator of the denominator. So this is what the denominator is, and again I have a factor of this, so C divided by 1 plus I. Now here I have a factor of 1 plus I in the denominator, and here I have a factor of 1 plus I in the denominator of the denominator. So I can basically cancel this out. If you feel this was very severe, just pause this video and think over it for a minute, and yeah, this is not that hard to see. And so what I'm left with is just C divided by I into this expression. This expression is 1 minus 1 plus I raised to a negative n. And as you can see clearly, raising it to a negative n is as good as taking the reciprocal, and so it's as good as 1 by 1 plus I raised to n, and everything matches with the formula that we have. So yeah, this is the proof for the present value of all the installments that we make.